Good morning, everyone. My talk today is not going to be as technical as probably most of the talks that you've heard, but I'm really hoping I can make a good case about why Julia is not only a fantastic tool for numerical computation, but it's also a very good interface platform to build computational tools in a shared research facility setting, where the end user doesn't necessarily know how to code or doesn't want to code, but they want to have full control of that code that they're given. Such shared research environments are increasingly common nowadays, especially in academic environments. I'm the scientific director of one of those at MIT, the Preclinical Imaging and Testing Facility. And what we do in this facility is we help labs all across MIT as well as surrounding startups to solve problems when their focus is to try to understand how to cure disease and how disease works for that matter. We are a multidisciplinary team from many different fields. Myself, I'm a physicist, but we have fields from biology, bioengineering, imaging science, and together with our technical staff, we provide services to researchers such as testing services, biomedical testing services, imaging instrumentation, and computation. So if I were to summarize just with one sentence what our goal is we help researchers and clinicians visualize and quantify things that they cannot see. And in that vast ecosystem of biotech and biomedicine, which really starts from a very fundamental level where an individual researcher will develop a novel compound or a novel device at the laboratory bench, all the way to the clinic where these compounds and devices are going to be used in patients, we place ourselves right in the middle at the so-called preclinical stage. So we take those compounds that previously have been evaluated, let's say, at a setting of a petri dish in cell culture, and right before they are translated into the clinic, and we are trying to evaluate them with a very strong focus in preclinical imaging. And just to give you a brief taste of what we do with imaging, this is a portfolio of images from our research. We are imaging biochemistry at a very fundamental level. For example, metabolism of glucose from tissues with a technique called positron emission tomography. You can see it moving from left to right. And that technique basically takes advantage of injectable radionuclides. In the second slide, and I wish we could dim the lights a little more so you can see them better, we can also image structure and morphology of vasculature. That's the example of that specific image, and for that reason we use microcomputerized tomography that relies on X-rays. Now, most of you are probably familiar with the third imaging modality, ultrasound, and if you're not, rest assured that, or at least I'm hoping that all of you have been subject to this type of imaging even before you were born. So with ultrasound, in our case, we are studying tissue function. And these green specks, if you can see them in the image, basically show how well vasculature perfuses blood. And in the very end, we are using magnetic resonance imaging, which we use in order to identify soft tissue and distinguish it from other types of soft tissue, as well as implants inside biological systems, how they distribute in the body, as well as some other physiological characteristics of them, oxygenation, pH, and so on. So from everything I've told you so far, you can probably imagine that we gather on a daily basis a lot of one-dimensional, 2-, 3-, and 4-dimensional data sets. And we organize them into multi-dimensional arrays, and our end goal is not only to visualize them, but also to extract some type of numerical quantitative information from that type of data. And our ability to do so in a shared research facility, such as the one that I'm working, is totally dictated by the amount of time we spend to produce this data, but also the amount of time it takes us to process them. As far as acquisition times, I'm giving here a rather naive breakdown of acquisition times with different imaging modalities. We can go all the way It ranges from a few seconds if we want to gather two-dimensional optical images, and we go all the way to tens of minutes for more involved imaging techniques such as PET and MRI. Of course, there is a lot of range fluctuation here. If somebody from MRI would see that, maybe they would complain that I blame MRI for being too slow. But we also have some extreme cases where acquisition times can go up to hours. Now, when it comes to data processing, so the data we get from these imaging modalities in order to process them, it's a little harder to pin a number to that. So I'd rather do that with a small example, and here I strongly encourage you to be completely agnostic as to the underlying science or biology or what we are trying to do here and why. I'm just going to guide you through a typical analysis pipeline. All you need to know about this image is just an MRI view of the abdominal area of a laboratory animal, and the little bright specks that you see are therapeutic implants. For that specific reason, we are trying to treat diabetes. And what you see here is just one view, one slice, from a typical 20 slices that we acquire. Now, if we really wanted to just visualize, we can stop right here. But as I mentioned before, if we want to become more quantitative, our analysis, our pipeline will be more involved. And in that specific application, that will imply acquiring that same image again and again by varying a specific quantity. Let's call it TI here. And what you see here is the same image acquired again and again when we vary this TI value. Here you only see 4 of these images, but typically we will acquire between 15 and 20. And then when we go to a pixel-by-pixel analysis in these images, we will produce tens of thousands of graphs like those, where the pixel intensity is plotted against this parameter that we value. And then we will try for every one of these graphs to solve a fitting problem, an optimization, more likely minimization problem, and extract the fitting parameter that we know is linearly proportional to the quantity that we are actually interested. So in this specific case, it's oxygen. So basically, following this analysis pipeline, we are able to transform spatial information that we get from MRI into some actual quantitative information, which is oxygenation. Now, most likely we would analyze this pipeline with MATLAB, and obviously not because that's the best tool to do so, but this is a tool very well familiar among the applied scientific and engineering disciplines. Many of our users are very familiar with it. And if we do so, obviously the analysis will be much slower compared to a low-level language compared to C or C++. Just to give you an example, for a 128 by 128 pixelated image, the amount of time it will take to analyze to do for just one image, and bear in mind that we collect hundreds of those in a single experiment, it will take MATLAB about 20 minutes to process. We move then to Julia, which we have done recently, and there the processing time, without any optimization, parallelization, all this fancy stuff that you can do, we were able to, sorry about that. We were able to minimize the processing time all the way to 1.5 to 2 minutes per data set, so almost reduce tenfold the processing time. So we were very excited about this, especially in a shared research environment where we provide this kind of research as a service, and timing is very important for us. Another thing that is very important when we translate MATLAB code that somebody else has written or some of our staff has written to Julia is that it's relatively straightforward to do, and that will imply increased compliance from our users to migrate to some type of new code. And the last thing, which is very, very specific to image processing, is that when we want to include libraries that read universal image formats, such as DICOM, we work with a lot of DICOM images, that might not be the biggest strength of Julia. The MATLAB engine or Python libraries are highly callable from Julia and makes it easy to do so without compromising significantly our processing time. So we are very excited about that. And the last thing is I'm going to close with a very recent, near future actually, effort from our facility, where we're trying to improve our pipeline to focus on decision making as well. I was very pleased to hear yesterday the afternoon keynote speech from Pfizer, where they basically showed the graph very similar to this one here. But the speaker was talking that in the clinical setting, there is not a lot of data. In a preclinical setting, such as the one that we work, there is a lot of data. We are a large repository of data that augments on a daily basis. So that will allow us to implement our Julia pipeline, as well as all the fancy new machine learning libraries and database libraries that you guys are building, in order to convert imaging from being informative in nature, which is unfortunately what it is right now, to rather predictive in nature, and be able to say whether a novel therapeutic will be able to make it to patients even at the preclinical stage. With that, thank you very much, and we are actively seeking for people to work with us on developing Julia platforms, so if you're interested in that work, please come find me afterwards. Thank you.
Thank you so much. Yes. Okay. Since we don't have a time for questions, please ask her questions after sessions, please. So our next speaker is